So we can go through this. This is an example of how an electric motor works, and we can see that if that in the first case here, this first case on the left, my magnetic. So what happens is my magnetic field exerts forces on this loop that want it to align so that it's perpendicular, like in this case. This is where the loop wants to be if there's current going through it. So in this case, I'm going to have a force up here and a force down here. And if I look at the current flowing, it's flowing like this. So if I curl my fingers in the direction of the current, then my thumb is going to represent the north face of the magnet, and I know the north face here is going to want to point towards the south. So I know I'm going to rotate clockwise here. In this case here, I have if I assume that maybe this is just a little bit of an angle, right? I'm going to curl my fingers in the direction of I, and the north face would be pointing towards the south. So if it rotates, it'll only rotate a little bit because it's almost perpendicular to the B field. In this case here, again my magnet, I'm going to be pointing down, and so here my loop is going to want to rotate up. It's going to want to rotate up towards the South Pole. In this case here, if I curve my fingers in the direction of the field, my north, my imaginary, my model for a magnet for the loop is going to be pointing up, and this is going to want to rotate all the way over to here so that it's all the way over to the south so that it's pointing. So I can tell from each of these pictures, by imagining my loop as a magnet, which direction my loop is going to want to rotate. So if I think about this, once my loop is aligned, like in this case here at B, once it's aligned like this, it doesn't want to move anymore. So once it gets here, it's all set. So what can we do to keep this motor turning? And one of the things that we can do is we can change the direction of the current. So here, the way that you do this is you use a commutator. And so what I do is I connect my loop of wire up to this split ring here, and the split ring is attached to a power supply. So I have a voltage, and then I have these brushes here that are connected on either side. And so what happens is as this rotates, as this starts to rotate, then I end up changing the direction of the current. So here I have my current is flowing this way, and then as this rotates, now the current is going to be flowing, because this side is going to be touching over here on the positive side, then my current is going to be flowing the other way. So every half a turn, my current is going to change direction, and so that's going to cause my loop to continually rotate in this magnetic field. You can also create a current in a metal plate if you move a plate through a magnetic field, and that's because my metal plate is made up of has charged particles in it, because those in a metal plate, my charges can move around. So if I take my metal plate and I move it, I'm actually moving a charged particle. So all of a sudden now I have moving charged particles. And so if I take that plate and I move it through a magnetic field, like in this case right here, I'm going to get current to flow. And so this represents the direction of the current flow in this region where the plate is going through the magnetic field. And we can also determine the current density, and it will be constant in the region of the magnetic field here. And so at the end of class, we're going to do magnetism worksheets 3 and 5.